Okay, good morning, grade 8. Our lesson today, we're going to continue the lesson of yesterday, chapter 7, lesson 4 in geometry, applying properties of similar triangles. We learned yesterday the first theorem that if a line parallel to a side of a triangle intersects the other two sides, then it divides those sides proportionally. Like this one, if EF is parallel to BC, it will intersect AB and AC proportionally. So AE over EC is equal to AF over FC. And also, we learned the opposite or the inverse or the converse of this theorem that says if a line divides two sides of a triangle proportionally, then it is parallel to the third side, like AE over AB is equal to AF over FC, then EF is parallel to BC. So yesterday we learned the theorem and its inverse. Today we're going to learn the third theorem in this lesson, which says if three or more parallel lines intersect two transversals, if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. Again, I'm going to read it. If three or more parallel lines like AB and CD and EF intersect two transversals like AE and BF. Let me color them so they will be clear. So the two transversals are A, C, and B, F. And the three parallel lines are AB and CD and EF. Then they divide the transversals proportionally. So now I have AC over CE is proportionally equal to BD over DF. AC over CE equals to BD over B over DF. Okay, girls. So let's watch a video here.
You know, another great theorem that's used a lot by artists is the two transversal proportionality theorem, which is like a mouthful, and maybe artists don't call it that, but they use this mathematical fact all the time. Let's take a look and see what it is together. So if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. In some sense, it's just sort of the extension of the other theorem we just looked at. So in this picture, I have three parallel lines, I have two transversals, and what I discover is that the ratio of this length to this length is equal to the ratio of this length to this length. Pretty cool. Now, we can actually see this happening in real life with an example. I'll put it up here on the side. So an artist used perspective to draw guidelines to help her sketch a row of parallel houses. She then checked the drawing by measuring the distances between the houses. The question is, what is one of those distances? So let me show you the picture. So here's the picture that she produced. And it's labeled, and you can see various lengths are given. And she wants to now see what is this length right here from Q to S. So that's the question. What is the length of Q to S? Well, we're going to use the two transversals
See,
proportionality
the parallel
theorem
lines
to solve
here
that.
are PT, QU,
So if we try this,
RV, and
we can
SW.
set up a proportion. Now, what do we have here? So I know I want to find this. And so what I have here is I know this length, that's good. So basically I can say this length is to that length as this length is to this length. But this length I've actually got to figure out. I know this is 6.7 centimeters. I know this length is 4.9 centimeters. And so when I add the two together, I see that this entire length here, UW, is actually 11.6 centimeters. And now let's put this information together. So I see 11.6 is to 5 as the thing I want, which is QS, is to that 5.8. So now I've reduced this sort of intricate drawing down to something that we can actually look at mathematically. Use the cross product. Cross product tells us that 5S is equal to 11.6 times 5.
Amir, we can't see the video.
Teacher, there is no video on the